Okay, for today's class activity, we're going to cover the introduction to gravity, so chapter 13, sections 1 through 4. We're going to cover these questions, so go read that in detail and try to apply those concepts and come here for some guidance with each one. So starting with concept question 1, the Earth's gravitational force on the Sun, is it larger, smaller, or equal to the Sun's gravitational force on the Earth? Answer is they're equal, okay? Because not only is Newton's third law say they have to be equal because they would be action-reaction pairs, but the law itself is very clear with F equals G m1 m2 over r squared. If you reverse the roles of the masses, you get the same value of the force, okay? So again, but even more broadly than that, third law says that this should be. Number 2. The gravitational force on a star on an orbiting planet is F1. Planet 2 is twice as massive, okay, and orbits at twice the distance from the star. Okay, so express F1 over F2. So you have two planets, one of a different mass and a different radius of orbit around the same star. How do the forces compare? Okay, we apply this, call F1 equals G. I'll put big M for the mass of the star, and then little m1 over r1 squared for the mass of the orbiting planet and the radius of that orbiting planet orbit. Then F2 be G, big M, that doesn't change, but its mass is twice as big, so it's 2m1. And its radius is twice as far, so 2r1. But we have to square that. So we get, this is equal to an overall 2 over 4, or 1/2, so half of F1. Okay, so F1 is twice as big as F2. Very good. Let's practice this proportionality in number 3. See if you can apply those same ideas of proportionality to number 3. Alright, so we have these two satellites. Satellite 1 has a mass of 1,000 kilograms and satellite 2 has a mass of 2,000 kilograms, or in other words, the mass of 2 is twice as big. Okay, but they follow the exact same orbit around the Earth. So, how do the forces compare? Well, if you just look at this, except this is the same radius, so we don't have factor here, we see that the force is twice as big on the heavier satellite. Okay, so F2 would be equal to F1. It's twice as big. But what about the acceleration? That's the second part of the question. What about the accelerations? How do the accelerations compare? Okay. Well, the acceleration doesn't care about what's being acted on. It just cares about what's doing the acting. Now, since they are at the same location too, there's the same pulling body, so it's or the Earth. So that's the same radius, so their accelerations ought to be the same. Okay, so now moving on to number 4. Okay, so with 4, we've got how far away from the Earth must an orbiting spacecraft be for the astronauts inside to be weightless? Do they have to be really far away? Technically, no. Okay. What does weightlessness mean? Well, we talked about that like when you're in an elevator, and if the elevator is falling, if the cable gets cut and you're inside an elevator, you can pick up your feet, and you're going to not move relative to the elevator because you're both falling with the same gravitational acceleration. So in orbits, weightlessness is simply that you, inside the spaceship, are all falling with an acceleration of g, whatever that g value is for where you're at. And so you could be right near the surface of the Earth. You're just flying in an orbit. You'd have to go pretty darn fast if you're close to the surface of the Earth to make an orbit. But you're constantly falling towards the Earth. It's just since you have a tangential, so here's your orbit, here's the Earth, your velocity is this way, but you're constantly being pulled inward. It's just your tangential velocity is big enough that you keep missing the Earth. As you're falling, but you miss the Earth, so you get pulled back in. So you're constantly falling. You were in free fall during this whole motion. And so it doesn't matter where you're at. If you're truly in an orbit around the Earth, then you're weightless the entire time. Okay? What about 5? It's a similar question. Okay? You have a hammer, and you're working on a spaceship, and you let go of the hammer. Is it going to fall to the Earth? It already is. So are you. So is the spaceship. Everyone is falling together, and so the hammer is going to sit there and fall right along with you, so it looks like it's weightless and just sitting there. So it's the same question. So no, it's going to fall together. Okay, now concept question 6 helps us focus on the difference about little g versus big G. Concept question 6. Okay, if you have the free fall acceleration, that's little g, okay, of some planet, I'm going to call it P1, is equal to 20 meters per second squared. Okay, this is a pretty big one. That's pretty big. That's a dense planet there. The radius and the mass of another planet are twice those. So the mass doubles and the radius doubles. How does G change for the other planet? G of planet 2. What does it depend on? Well, it depends on big G. It depends on the mass of the planet, which is twice m1. And it depends on the radius of the planet, which is twice r1. Okay? And so G is going to end up being half, because we'll have 2 over a 4 gives us a half. So that's going to be 10 meters per second, because it's half of what this one would be. Remember, little g is defined as the big G, the universal constant, times the mass of the object times the radius of the object. Okay? And here we're referencing this is at the surface of the planet, where we plug in the radius of the planet. Okay, very good. Now let's move on to some exercises. Exercise 3. Okay, we have 2 lead balls. We have a 10 kilogram lead ball, and we have 0.1 kilogram lead ball, and they're 10 centimeters apart. Okay. And the question is, what is the gravitational force between them? Well, we're going to apply our universal law of gravity. Okay, which is the gravitational force between any 2 objects with mass. So we have this gravitational force. We just plug in 6.67 times 10 to the negative 11 times 10 times 0.1 divided by 0.1 squared. And we're going to end up with a fairly small force, which we'd expect because this gravitational constant is so small that it takes planetary-sized objects to have a significant effect. Okay, now question 2 is kind of fun to think about. How big is that? The gravitational force on the smaller mass, the 0.1 mass, is just going to be mg. So Fg is just mg, and g is 9.8. It's at the surface of the Earth. Okay, so technically that would be a g sub e. All right. And what is the ratio? How much smaller is this? So if you take this divided by this, plugging 9.8 times 0.1 in, you end up with the F we calculated is equal to 6.8 times 10 to the negative 9 Fg. So it's a heck of a lot smaller. Super, super small. Okay. All right, so now moving on to 12. 12. Okay, we have a newly discovered planet. Okay, and it is twice as large and 5 times as massive. So its mass is 5 times bigger. Its radius is twice as big. What is the free fall acceleration on its surface? And that's twice as big as the Earth. Okay. So its free fall acceleration, we'll call it g sub p for this planet, it's going to be equal to this universal constant, the mass of that planet, which we were told is 5 times as big, so it's 5 m of the Earth, okay, and then divided by twice the radius of the Earth, which we square, which that will pull out a 5 over 4, leaving behind just our normal g. So 5 over 4 times g of the Earth, 5/4 of 9.8. Okay, so again, what is little g? Little g is the gravitational acceleration of an object, but it depends on what object's doing the pulling and where you're measuring it at. And generally we refer to it at the surface, so we plug in the radius, but not necessarily. Okay, moving on, number 14. Okay, so here we have planet Z as a radius, and we know its free fall acceleration. It's 8, so it's similar to the Earth, a little bit smaller than the Earth. What's the mass of planet Z? We use this same idea. We define, here's planet Z, is g mz over rz squared. We know this is 8. We know this is 10,000 kilometers. Now note that's kilometers, which means it's 10 million meters. Okay, 10 times 10 to the 6 meters. We have to square that. And we can find this mass. This is just solving for that mass. We get mz is equal to 1.2 times 10 to the 25th. Which is similar, a little bit bigger than the mass of the Earth. Okay, that was part A. Part B is, what is the free fall acceleration when you're 10,000 kilometers above the surface of planet Z? Well, so it's saying, since the radius is 10,000 kilometers and you're that much higher above, that means the distance from the center to you is twice the radius. So G at 2RE, okay, at planet P. All right, sorry, that was Z, not planet Z, not Earth. I apologize. So we just plug in G mz over 2RZ squared. We end up with 1/4 whatever we had before, which was 8. So we get 8 over 4 gives us 2 meters per second squared. So you can see it really does matter. When we start getting really far away from the surface relative to the radius of the surface, it drops significantly. So we have to be careful. Okay, now let's move on to applying some of these concepts and taking care of the geometry of the problem. This is number 35. Okay, now 35 is simply going to focus on this equation, but we need to remember it's a vector. Okay, and so we're going to need to deal with components. We're going to find the magnitude of the force, but it's going to be first finding components. So we have a system where we have a 5 kilogram mass, which I'm going to call m, and it is a distance I'll call 2d above a 20 kilogram mass, which I'm going to call 4m, which is 10 centimeters away, which I'll call d, from a 10 kilogram mass, which I'll call 2m. All right. Part A of this problem is to find the net force acting on this 20 kilogram mass. Okay. The net force, what is the total force, and what direction does it point? Okay. So, thinking about that, let's get that direction first. We can think about that direction qualitatively. This is 5 kilograms, and it's straight above it, and it's 2d apart. This is 10 kilograms, so twice the mass, but half the distance. So how much bigger is the force pulling it this way than the force pulling it this way? Okay, the force pulling it this way is twice as far, and it's half the mass, and so it's going to be a lot less, by a factor of 8, in fact. Okay, because the distance squares, and then the mass goes linearly. So we get a factor of 8 smaller. So this one's going to totally dominate. But there's a noticeable effect from this one. So we know that the direction the net force ought to be is something closer to this one, because this has a significantly larger force. Okay, and so I'm going to just define that angle to be theta 1. Okay, so let's find this force. Okay, to do so, we need to find components. So we first find Fx. Alright, now Fx is going to point this way, that is Fx, and Fy is going to point this way, Fy. Alright, and so Fx, we'll choose that to be positive and up to be positive. Fx is going to be g, the mass of the one acting, which is 2m, times the mass of the one being acted on, which is 4m, divided by the distance between them, d squared. And that's in the positive x direction, which I'm implying with the subscript here. Well, what is Fy? Fy, positive, and it's g times the mass of the object acting, so that's m, times the mass of the object being acted on, 4m, divided by the distance between them squared, so that's 2d squared. Okay, so let's simplify these. You can see why I've done it in terms of m and d. This becomes 8 gm squared over d squared. Okay, this one becomes, we got 4 over 2 squared, which is 1. So this is just gm squared over d squared. And now that I have those components, I can find this angle, because this is the vertical piece, that's this piece, that's opposite theta 1. This is the horizontal piece, or the adjacent piece, and so that theta 1 is going to be inverse tangent of the opposite over adjacent, so this one over that one, but you can see this one's just 8 times bigger than this one, so I just get a 1/8. Okay. And if you plug in your number, you get a pretty small value. You get, oh, where did I put my number? There it is, 7.1 degrees. Sorry, I can find it on my sheet. 7.1 degrees, which is what we kind of guessed. We guessed it's going to be much, much closer pointing this way. So that is reasonable. Okay, and then how big is that force? Well, this is going to be taking the square root of the sum of the squares. So we go F is going to be equal to Fx squared plus Fy squared. Okay. If you plug on all your numbers, you can do some simplifications pulling out the common factors. But if you plug in all your numbers, you'll end up with 1.34 times 10 to the negative 6, which I'm not sure if it's that big or 10 times that big even, but I know it should be small. It should be quite small. So I've got this value as being fairly small. Okay, so I've got those and they seem reasonable. Alright, now that one was a good practice of components, recognizing we had to find the force in the x and the force in the y, and then bring them together to find these values. Now part B helps us practice with yet one more thing with vectors that we need to remember. With all vectors, we have to really get this process down. It's now saying, well, what's the force, net force acting on this mass, this 5 kilogram mass? So this is the one now being acted on by these other two. Okay, well, let's just redraw that to make it clear. We have this mass, and we have this big one here, this small one here. So this one is closer and bigger, so that's going to be a fairly large force. Okay, it's going to be a fairly large force. This one is smaller and further away, so it's going to be a smaller force. Okay, but what's important is I need to add these vectorially, which means I need to break this one up into a horizontal piece and a vertical piece. Okay, I need to calculate those pieces. So if I go ahead, let's try and make this simple. I'm going to call this theta 2 there. Okay, so I could bring this piece here and put it down here. So I'm going to have a triangle that looks like this. Okay. And this will be the x component of this one. We'll call this one 1 and 2. This will be 2x, and this will be f2y. And so I need to know this theta to be able to find those two pieces, okay, how big it is. Because I can find how big this one is by the full form. All right, so to find f2x, I need to say this is going to be f2, and that, my x, from the angle I chose, is sine, because it's opposite, sine of theta 2. Well, what is f2x? Well, it is, this is r, this is one being acted on, so my r vector points this way, r hat, this will be r2. Okay, the distance, that's the total distance, which again, this is 2d, this is d. So that is going to be the square root of the sum of the squares of these two sides. Okay, so I'm going to have g, the acting one is 2m, the one being acted on is m, divided by the distance between them squared, which is just this squared plus this squared. Well, this squared is 4d squared, this squared is d squared, so that gives me 5d squared. Okay. So that's the full force. It's divided by the full distance squared, this full distance. And then I tack on a sine of theta 2. Okay, sine of theta 2. Oops, sorry. Not squared, but theta 2. Well, how do I find theta 2? Theta 2 can be found from this same triangle. This is the same triangle. And theta 2, I know the opposite and adjacent sides. I also know this side. And so I could use, well, sine of theta 2 would be opposite over hypotenuse. And hypotenuse is square root of 5d. And so I could use that to find it. So basically I can use geometry to find this theta 2. Okay, and so I can plug that into there. And if you do, you're going to get theta 2 is equal to 26.565, which I leave a lot of digits because I'm not done with this. I have to calculate other things. And so I can use geometry to find that. There's other ways where I can recognize, well, sine of theta 2 is opposite over hypotenuse, so I can just plug in d over d square root of 5, which the d's cancel, I get 1 over square root of 5. That's another way of doing it, which is nice. But I've seen students get confused with that way. So I like to just find the sine of that angle and multiply it by the full vector. Okay, now that's how we'd find f2x. We need to find f2y. In the same manner, it'd be g 2m times m over 5d squared, the full vector, but now it'd be times cosine of theta 2. Okay, and I can find those two. Now, the question is, what is the net force on this from both of these? What I've found here, I've just decomposed this one vector into its components. What do I do with them? Well, now I need to add this one with the one from this force, which we've already calculated. That's this right here, because it's the same force, it's just between these two. So now I can take this one plus this one as my full F net Y. They're both downward, so that's going to be, I'm going to pull out, I've got a g m squared over d squared times the 2 over 5. I'm going to pull out a g m squared over d squared, and I get a 2 over 5 cosine of theta 2. That's taking this one plus this one, which is just 1. There's just all these numbers times 1 right there. And that's my net force in the y. I had to add the y's together. F net x Well, that's just this one. There's no more other forces pulling the x, so that's just this one. Gm squared over d squared times 2/5 sine of theta. Okay. And now I have the x and y components of the net force acting on this object. So this is a lot of review of vectors, and I just want to make sure it's clear. We did a lot here. We just reviewed, okay, we just combined two vectors together that are already broken up. One is x, one is y. But here, we had to take a vector that is at an angle and break it up into components, which we did by finding the full vector times sine or full vector times cosine. And then, to find the net force, we had to add the downward forces together to get the net force in the y, and in this case there's only one x. Okay, so this is a big review problem of how to do vectors. We've done this with other things, but now we just have a new force law that we're playing with. Okay, so I'm going to leave the actual algebra of combining these the same way we've done up here. I'll just give you the answers. If you plug in your numbers, you're going to get that the force, the net force acting on this one by these two, is equal to 2.3 times 10 to the 7th. Looks like I'm running off the page there. Okay, 2.3 times 10 to the 7th, negative 7th, or sorry, yes, negative 7th kilograms. These are little masses, not planets, so it should be small. And that the angle that the sum of the vectors makes, so that's not theta 2, but now that's the combined direction, the net force. So we're going to get some net force, and relative to down, I'm going to call that phi. Phi would equal 7.5 degrees right of down. Okay, and again, we should expect it to be small because this one is big and closer than this one, which is also small. So this should be a much bigger effect. Okay, that is it.